Okay, welcome students. In the first class, we discussed about valence bond theory VBT by Linus Pauling and Slater. In that class, we discussed about valence bond theory, different types of overlapping, sigma and pi bonds, and the concept of hybridization, and three hybridization, sp3, sp2 and sp. And we also discussed the shapes of three molecules: methane, boron trifluoride and beryllium difluoride. In this class we will discuss about a new hybridization involving d orbital. For that purpose we can take a simple molecule, phosphorus pentachloride. What is the shape of phosphorus pentachloride? What is the nature of the bond, phosphorus chlorine bond? So we can take phosphorus pentachloride, PCl5, phosphorus pentachloride, phosphorus pentachloride. Five phosphorus chlorine bond. 1, 2, 3, 4, 5. 5 phosphorus chlorine bond. How these bonds are formed? Whether all these bonds are same or different. What is the shape of this molecule? So a new hybridization involving d orbital. So central atom phosphorus. Atomic number 50. Main shell configuration 285. 5 electrons in the valence shell. So configuration 1s2, 2 electron, 2s2, 2p6, 8, and 3s2, 3p3 and 3d0. And this is the valence shell, outermost shell, valence shell. And this electronic configuration is called ground state electronic configuration. Ground state electronic configuration. Valence shell. 3s2. This is a paired orbital. And 3px, 3px, 3py, and 3pz orbital. And 1 electron, 1 electron, 1 electron. 3p3. And 3d0. 3d0. D possesses 5 orbitals. 1, 2, 3, 4 and 5. Maximum capacity 10. 5 orbital. 3d0. And this is the ground state electronic configuration of phosphorus. The ground state. So the valence orbital, 3s orbital is fulfilled and it is paired. So 3 orbitals are half-filled. So in the ground state, its valence is 3. Only 3 orbitals have a combining capacity. Half-filled, half-filled, half-filled. So in the previous class we discussed a covalent bond is formed by orbital overlap containing unpaired electrons with opposite spin. That is the valence bond theory. So half-filled, half-filled, half-filled. Valence is 3. Actually phosphorus is pentavalent. So in order to expand the valency to 5, one of the 3s electrons promoted to the vacant 3d level, and that state is called excited state. So one of the 3s electron promoted to the 3d level, that state is known as excited state. So excited state electronic configuration, that is 3s1, because one of the electrons is promoted to the vacant 3d level, and this is p level, and 3px1, 3py1, 3pz1, and 3d also 1. 3d1. 1, 2, 3, 4 and 5. 3d1. This is the excited state electronic configuration. So after excitation, what happens? So these orbitals, so we discussed the concept of hybridization in the first class, and these orbitals are with different shapes. This is dumbbell, and this is s orbital is spherical, and all these orbitals are dumbbell, different shapes, and they possess a slightly different energy. and this is 3s and 3p and 3d. The valence orbitals, there is a slight difference in their energies. So they are with different energies and with a different shape. The valence shell of phosphorus, they undergo an intermixing. That phenomena is called hybridization to produce orbitals with the same energy and same shape. So all the orbitals undergo a mixing. That phenomena is called hybridization. One s orbital, 3p orbital and 1 d orbital, and this hybridization is called sp3 dehybridization. So how many orbitals are involved? 5 orbitals, 1s, 3p and 1d. According to hybridization, how many new orbitals are formed? Same number, 5 new orbitals are produced. 5 new orbitals and 1 spherical and 4 orbitals are dumbbell. So the newly formed orbitals are dumbbell shaped orbital. So how these dumbbell shaped orbitals are oriented in space to minimize the repulsive force and to attain a maximum stability. According to VSEPR theory, these 5 orbitals are oriented along the 5 corners of a trigonal bipyramid with bond angles 120 degree and 90 degree in order to minimize the repulsion between electrons and to achieve a maximum stability. The orbitals oriented like this. 3 orbitals along the 3 corners of an equilateral triangle. 3 orbitals along the 3 corners of an equilateral triangle, 3 electrons, and phosphorus, 3 orbitals with a bond angle 120 degree, and the remaining 2 orbitals in the axial position with a bond angle 90 degree, and this is shape is called trigonal bipyramid. 3 orbitals, 3 corners of an equilateral triangle, 3 orbitals, one above the plane, another below the plane with a bond angle 90 degree. One above and another below, the bond angle 90 degree. So 2 bond angles 120 degree and 90 degree, and phosphorus undergo which hybridization? sp3 dehybridization. Now phosphorus is ready with 5 orbitals to receive how many chlorine atom? 5 chlorine atom. All these orbitals are half-filled and these orbitals are called sp3d hybrid orbitals, and all orbitals are with the same shape and same energy, and they are ready to receive 5 chlorine atoms. So discussion is, the first discussion is for 11th and 12th class students CBSE, and you listen here. 5 hybrid orbitals, and these 5 hybrid orbitals orientation along the 5 corners of a trigonal bipyramid with a bond angles 120 degree and 90 degree. Phosphorus is ready for an overlap with 5 chlorine atom, 5 orbitals and 5 chlorine atoms. Okay, second part, orbital overlap. Second part, first part, hybridization of phosphorus. What is the hybridization? sp3d. How many orbitals are formed? 5. Orientation along the 5 corners of a trigonal bipyramid. Bond angles 120 degree and 90 degree. First part, hybridization. Second part, orbital overlap. Chlorine comes with its orbital and its overlap with this hybrid orbital, and 5 pairs of bonds are formed. So this is phosphorus with 1 electron. Phosphorus with its 5 electrons. 1, 2, 3, 4 and 5. These 5 electrons are now present in 5 orbitals. Now chlorine, each chlorine will come with 1 electron. We can, so the first part is hybridization of phosphorus, this central atom. The incoming atom will come with its pure orbital. So we can check which is the orbital of chlorine to coming to overlap with this hybrid orbital of phosphorus. So chlorine atomic number 17, configuration 287, outermost shell 7 electron, shortage of 1 electron to achieve stable noble gas argon-like configuration. What is the configuration of argon? 288. So chlorine has a, not only chlorine, all halogens have a shortage of 1 electron to achieve stable noble gas configuration. Valence shell 7 electron. So the orbital wise configuration: 1s2 stable, 2s2 stable, 2p6 stable, 3s2 and 3p5. 3p5 valence shell 7 electron, shortage of 1 electron in which subshell? 3p subshell. So 3px, 3py, 3pz, 3p subshell, total 5. 2, 2, 1, shortage of 1 electron. When this 3pZ1 becomes 3pZ2, this 7 becomes 8, and the atom achieve argon-like configuration. So phosphorus ready, and chlorine will go with this 3pZ1 orbital to overlap with phosphorus atom. So 3pZ dumbbell shaped pure orbital, dumbbell shaped orbital with 1 electron. This is chlorine's valence orbital. So phosphorus 5 orbitals, same figure. Chlorine, phosphorus, the axial position above the plane and below the plane. These 3 orbitals are in the same plane, and these 2 orbitals above and below the plane of these 3 orbitals. Bond angle 120 degree, bond angle 90 degree, carry 1 electron, hybridization sp3d, phosphorus. Chlorine with 3pZ, 5 chlorine will overlap. The valence bond theory, orbital overlap. Orbital overlap. Chlorine, last orbital 17, 3pZ1. Dumbbell, pure p orbital. Overlap here with an electron. Chlorine. Chlorine. PCl bond, a pair, bond to pair. Another chlorine. We can extend this line. Another chlorine here. Phosphorus chlorine bond. Phosphorus chlorine bond. Phosphorus chlorine bond. Phosphorus chlorine. And phosphorus pentachloride is produced. This is PCl5. So this is a sp3d orbital, hybrid orbital. Each orbital is called the sp3d hybrid orbital for 11th and 10th class students. And this is sp3d orbital, and this is a p orbital of chlorine. So overlap sp3d p overlapping. sp3dp, this covalent bond, orbital overlap. This is also that same sp3d p overlap. sp3d p overlap. So PCl5 is produced. Phosphorus is under this orbital is called the sp3d hybrid orbital. Chlorine p orbital, 3p is at p orbital, and phosphorus pentachloride is formed. So PCl5 molecule. Hybridization sp3d. So what is sp3d hybridization? If 1s, 3p and 1d orbital are involved in an intermixing, that hybridization is called sp3d hybridization. Here 5 hybrid orbitals are formed. These hybrid orbitals are oriented along the 5 coordinates of a trigonal bipyramid with bond angles 120 degree and 90 degree. So here in PCl5, phosphorus is under sp3d hybridization. So stereochemistry shape of this molecule is a trigonal bipyramid. 2 bond angles, 120 degree and 90 degree, 120 degree and 90 degree. Okay, we can take the molecule again. About phosphorus pentachloride, this is enough for 11th class students. Shape a trigonal bipyramid, 2 bond angles 120 degree and 90 degree. For higher level examinations or entrance examination, we look again. So phosphorus pentachloride, PCl5. This is PCl5. These 3 chlorine atoms are present in the same plane, and these 3 chlorine atoms are called equatorial chlorine atoms. 3 coordinates of an equilateral triangle. So equatorial chlorine atoms. These 3, they are in the same plane. These 3 chlorine atoms, equatorial chlorine atoms. These 3 chlorine. And these 3 covalent bonds, 1, 2, 3, are called equatorial bonds. So 3 equatorial bonds are present in PCl5. These 2 chlorine atoms are called, they are present in the axis. Right angle 2. these equatorial bonds at an angle 90 degree. And these two chlorine atoms are called axial chlorine atoms. Axial chlorine atoms. And these two covalent bonds, this bond and this bond, is called axial bonds. Question, axial bond. A. So we can divide the 5 covalent bonds in PCl5 into 2 types. They are equatorial and axial. So 5 bond in PCl5. 3 equatorial and 2 axial. 2 axial bond. 3 plus 2 is equal to 5. Total bond 5 bonds. 5 sigma bonds. They are divided into 2. Equatorial bond and axial bond. This is enough for higher secondary level. Plus 1 plus 2 level. This is sufficient for state syllabus and CBSE. 2 types of bond. Another point. From electron diffraction studies, it has been found that the axial bond is somewhat longer than this equatorial bond. So we discussed all bonds are sp3dp overlapping. All bonds. And in the first sense we think all bonds are identical, same. Because hybridization is sp3d of phosphorus. Each phosphorus produces 5 sp3d hybrid orbitals, and the chlorine atom overlapped with these hybrid orbitals, and all the 5 orbital overlap are sp3dp overlapping. So all bonds should be same. But electron diffraction studies shows that this bond, axial bond, is little longer than this equatorial bond. This bond is short, this bond is long. And the axial bond length was found to be 219 picometer or 2.19 angstrom. 219 picometer. And this equatorial bond, these 3 bonds found to be 204 picometer. A slight difference of 15 picometer difference. So the final discussion, PCl5 hybridization sp3d trigonal bipyramid. We divided that 5 bonds into 2 categories, equatorial and axial. And from experiments, electron diffraction studies shows this bond, axial bond, is somewhat longer than, little longer than this equatorial by an amount 15 picometer. What is the reason for this? What is the reason? Why this bond elongated? Too long, 15 picometer. Bond becomes long means the pair of electrons present between them becomes delocalized. They can break very easily. When bond length increases, the bond strength decreases. You can very easily break when bond length increases. When atom very come closer, a strong intimacy between the electron pair and the atomic nuclei. 2 atoms, 2 nuclei, a pair of electrons between them. The 2 atomic nuclei attract the pair of electrons very closely, and the bond becomes strong and the bond length decreases. They come very closer. When bond length increases, when atoms are far away, a pair of electrons, a little attraction. The attraction between the nuclei and the pair of electron decreases, and thereby bond strength, we can very easily dissociate that bond. We can dissociate that bond very easily when bond length increases. This is a 219 picometer. This is only 204 picometer. So we can very easily break these 2 bonds. So when PCl5 is unstable molecule, When simple heating, it dissociates into PCl3 and chlorine. Cl2. Which is the Cl2? Chlorine atom in the axial, chlorine atom in the axial, and this is the Cl2 molecule. This bond is longer. Experimentally, it is proved. Electron diffraction studies shows this bond is long than this bond by an amount of 15 picometer. So what is the reason for this? So we can discuss that. The elongation of the axial bond and the shortening of the equatorial bond. Two bond length. So we discussed the simple way. sp3dp, sp3d-p hybridization. All hybridization, all overlapping are equal. But finally, experiment, this is theoretical by Linus Pauling and Slater. Experiment shows two bonds are longer than other three bonds by an amount 15 picometer. So experimentally shows that PCl5 is unstable. It decomposes into PCl3 and Cl2, these two chlorine atoms. Two reasons we can explain in simple way. First, in a simple way, degree level students, for high grade entrance examinations. So again PCl5, PCl5, PCl3, equatorial chlorine atoms at an angle 120 degree between equatorial chlorine atoms between at an angle 120, 120, 360, 120, 120. They are at an angle 120 degree away from each other. And axial chlorine atoms 90 degree above, 90 degree below chlorine. So at an angle 90 degree between this axial and equatorial, 120 degree far away, very close, very close, very close, very close, 90 degree. We can take this one for the discussion. So chlorine outermost shell 7 electrons, 7 electrons, 7 electrons in the outermost shell of chlorine. 2, 4, 6, 7. This pair is called a lone pair. Here also 7 electrons. 1 electron take parts in the covalent bond formation, and the remaining 6 electrons, 3 pairs. This lone pair and this lone pair undergo at an angle 90 degree. At an angle 90 degree, 90 degree. So the axial hydrogen and equatorial, the axial chlorine and equatorial chlorine at an angle 90 degree. So they undergo a Coulombic repulsion, lone pair repulsion. Lone pair, lone pair, lone pair, lone pair repulsion leads to the extension of this bond, repulsive force. That is one of the reasons for the elongation of this bond, because these axial chlorine atoms are at an angle 90 degree. So instead of chlorine, in the examination they can ask phosphorus pentachloride. Same discussion. PX5. Now we are discussing phosphorus pentachloride. Phosphorus pentachloride also same discussion. That is why this bond becomes large, longer than this bond. So 219 picometer and 204 picometer. One of the reasons for the elongation of the axial bond. So another reason, after a degree. For high grade entrance examination. So look, the excited phosphorus, 3SO1, 3PX, 3PY, 3PZ, excited phosphorus with a star, 1, 1, 1. And this is 5 d orbitals, 1, 2, 3, 4 and 5 d orbitals. Say it is a 3d. Suppose this orbital is 3d Z square. What are the 5 d orbitals? dxy, dxy, dxz, dyz, dx square minus y square and dz square. dz square along the axis. These are between the axis like this. Another class we can discuss their shape. And this is also dx square minus y square along the axis. This is along the axis, this orbital. So, why that axial bond is longer than the equatorial bond? So, this is the excited state of, look at this. This is dz square orbital. I am taking this dz square orbital. Remaining 4 orbital. 1, 2, 3 and 4. So I am avoiding that orbitals. I am taking only this dz square orbital with 1 electron. Why the axial bond becomes longer than the equatorial? At first, they undergo sp2 hybridization and 3 orbitals. 3 orbitals. 3 hybrid orbital sp2 along the 3 corners of an equilateral triangle. 1 spherical and 2 dumbbell sp2 percentage 33% s character and 67% p character for each orbital. sp2 hybrid orbital 1 spherical and 2 dumbbell percentage 33% s character spherical character and 67% p character for these 3 orbitals. Bond angle 120 degree. Atom phosphorus. Hybridization sp2 plus these 2 orbitals undergo mixing 3pz and 3dz 100% p 100% dumbbell 100% dumbbell no s character. So dz plus pz mixing. No s character, 0 s character. The 2 orbitals, 3 orbitals gives 3 orbitals. These 2 orbitals mixed together and produces 2 orbitals. Both are purely dumbbell because no s character, 0 s character. So 2 orbitals and in the axial position, no s character, bond becomes only p. Dumbbell. 33% s character. Orbital becomes small due to high s character. High s character, maximum mixing, maximum overlapping. And this orbital becomes, these 3 orbitals become small because 33% is spherical character. Spherical character means maximum overlapping. Maximum overlapping means orbital becomes small. Here there is no s character. 100% p character. 2 orbitals, not 1 orbital, 2 orbitals. 2 orbitals mixed. The 2 orbitals are produced to carry 1 electron. This is the axial orbital. And sp2 plus dp. This is a dp hybridization. So sp3, p2 and p, sp3 d hybrid, totally sp3 d hybridization. And this orbital has a 0% s character in the entrance examination. The orbital lying in the axial position of phosphorus pentachloride, PCl5, in the trigonal bipyramid, the orbitals lying in the axial position has how much s character? 0% s character. And the orbital in the equatorial position, the s character is 33% s character. S means spherical, maximum mixing, maximum overlapping, and orbital becomes small. Only p character, elongated dumbbell. And this orbital is longer than these 3 orbitals. And here chlorine will come. 2 bonds will produce. And 219 picometer. And these 3 orbital, 204 picometer bond length. And this bond will break easily into PCl3 and Cl2. And this is the another reason they, one of the examinations they asked which orbital of phosphorus, 3d orbital of phosphorus mixed with p orbital of 3p Z orbital of phosphorus, that is dz square orbital. Orientation along the axis. This P also orientation along axis. This is 3dz square also along the axis. Their mixing is very easy, and thereby dz square orbital will take parts in the mixing. So that is the answer, dz square with 3pz and 100% p character, no s character, 0% s character for this orbital. For CBC student, I discussed this orbital is called sp3d orbital. 20% s character, 20% d character, and 60% p. In that way, we discussed it. For that CBC class, that is enough. But actually, in our discussion, this orbital is called sp3d orbital. 20% s, 20% d, 60% p, sp3d. But actually, these two orbitals have only 0% s character. Okay. That is why phosphorus pentachloride readily undergo dissociation. It's an unstable molecule. That elongated bond is unstable bond. By supplying lesser amount of energy, we can break the two bonds. So PCl5 dissociated into PCl3 and chlorine. So in organic chemistry, conversion of alcohol into RCl, we are using PCl5. This PCl5 OH is replaced by chlorine atom from the axial position. ROH, alcohol is into alkyl chloride very readily. PCl5 supply its axial chlorine atom very easily. Carboxylic acids can be converted into acid chloride. This OH can also be replaced by using PCl5 because it readily decomposes and supply these two chlorine atom. This OH can be replaced by this chlorine atom, acid chloride, alcohol, alkyl chloride. Okay, thank you.